All right, so in this chapter, we're going to start looking at the structures of different molecules. We'll talk briefly about ionic and covalent bonding again. Um, but we're going to start to figure out how we can go from, and for the most part, we'll be spending time figuring out how we can go from a chemical formula, and then actually using that to determine what the structure of that molecule is going to look like. And there's going to be a couple different steps through that process. So first, we'll just kind of get the general arrangement of those atoms and electrons. So what's bonded to what? Where do we have lone pairs, single, double, triple bonds? And we'll talk about what all of those different things are if you're unfamiliar with them. And then we'll talk about how we can go from kind of just that general sort of framework of the molecule. We'll see why it's not a true representation of what it really looks like, but how we can go from that version of the molecule to a more accurate three-dimensional sort of depiction of it. And then ultimately, we'll see how does the structure influence the properties of whatever that substance may be. Because when we look at the picture on the left here, this is just a Buckminster fullerene molecule, so C60, so it's just 60 carbon atoms. And then if you look at it, you can see in some cases, we've got kind of a hexagon. So we've got double bonds. So you can see the two lines between the circles are representing the carbons, and single bonds. And then in other cases, a little tougher to see, but we've got pentagons. So it's why we've got the soccer ball here. We see a similar shape. So we've got 5-sided shapes, 6-sided shapes, just in a collection together. But like I was saying, the structure of these molecules influences the properties, because when we look at a buckyball like this, like I said, it's just C60, so it's just 60 carbon atoms. But when we think about diamonds, when we think about the graphite in pencils, both of those are also just carbon atoms as well. But because they're going to be in a different arrangement, they're going to be a different structure. That's why we see different properties between those. And again, in just those cases, it's only carbons. We're going to see with some of these different molecules we'll look at in the chapter, we're going to have a collection of atoms. So it won't just be carbon. In some cases, we'll have hydrogen, oxygen, fluorine, whatever it may be. But we'll see the steps how we can go from that chemical formula to the true three-dimensional structure. And with this, we're going to be using what are known as Lewis symbols. Lewis symbols is just specific when we're looking at a single atom. When we actually start looking at molecules, collection of atoms, it'll be a collection of Lewis symbols, and in that case, we typically refer to as a Lewis structure. But it's just referred to as a Lewis symbol because it's named after Gilbert Lewis, who kind of came up with the idea. And with these Lewis symbols, they're going to be relatively straightforward in terms of just kind of what do they look like. And we can see an example here with oxygen. But in each case, we're going to have the element symbol just in the middle. So in this case, since it's oxygen, we just have the O. But that symbol, that letter, or if it's something like lead, Pb, whatever it may be, that letter or two, that symbol is going to be representing the nucleus. It's also going to be representing all of the inner electrons. So in this case, the O would be representing the 8 protons for oxygen. If it's oxygen 16, it would also be representing the 8 neutrons in that nucleus. But then when we look at the electrons here, the electron configuration, I should say, we've got 1s2 and then 2s2, 2p4. So 2s2 and 2p4, those are going to be our valence electrons. That's why we've got 6 dots around here, because each of these dots is going to represent a valence electron. And the reason we're only interested in those valence electrons, or we're only representing the valence electrons, is because remember, those are going to be the outermost electrons, the highest energy electrons in that atom. So those are going to be the electrons that participate in chemical bonds and chemical reactions and things. So those are going to be the ones that we're kind of focused on. But the 1s2 electron in this case, or any of the inner electrons, depending on what element we're looking at, are going to be sort of implicitly shown with just that symbol. So like I said, the O in this case is representing the nucleus. It's also representing the 1s2 electrons. They're still there. They're still important for the structure of this atom as a whole, but we're only going to be interested in the valence electrons. And then if you remember from the previous quarter, we talked about orbitals. Each orbital can hold 2 electrons at the most. So when we're looking at these symbols, we can kind of treat the symbol as having four sides, top, bottom, left, and right. And then with it, we'll see kind of the pattern for how we can fill these in. But we've just got four sides. So as we add the electrons, we're just going to add a dot to a different side all the way up to the fourth one. So you can see sodium. This is just moving across the third period, I should say. So sodium to argon, element 11 to 18. But as we go from sodium to magnesium, we gained one electron. So that's why we've just got one extra dot. But then we're also changing the symbol because now we're representing magnesium rather than sodium. Same thing as we go to aluminum. Change the symbol. Now we've got one extra electron. So that's why we've got a third dot around this aluminum. Silicon has a fourth. And then now when we get to things like phosphorus, sulfur, chlorine, argon, 5, 6, 7, and 8, now we're going to start doubling them up, excuse me. And with it, just to go back for a second, all four sides are equivalent. So we'll see in the next chapter exactly why that's the case, why we don't really have to specify like which of these is a s orbital, which of them is a p. We'll see why it doesn't really matter in terms of these symbols. And because of that, it doesn't really matter which side you put the dots on. So this is showing starting on the right and then adding to the left, the top, and then the bottom. You could have as easily put the first one on top. You could put top and then right, top and left, whatever it is. The important thing is just to have the correct symbol in the center and then the correct number of dots on either side. And we just don't want to have more than two once we get to like 5, 6, 7, and 8. 2 electrons on a side, I should say. But with this, since we're only showing the valence electrons, as we move down any group, the Lewis symbol for all the elements in a given group are essentially going to be the same. It's only the symbol itself in the middle is the only thing that's going to be different. So if we think about like lithium and sodium, both of them are group 1 elements. Both of them are alkali metals. So you've got 2s1 or 3s1. So because they each only have a single valence electron, that's again why they have similar properties, but that's also going to be why they each only just have that one dot. And if we continued down group 1, we would see the same thing with potassium. It's just instead of Na or Li as the symbol in the middle, we would just have K for potassium. And then we can see the same thing, group 2, beryllium and magnesium. Each have 2 valence electrons now, so they each have the 2 dots. Boron and aluminum have 3, and then we can see kind of that same pattern all the way down. And with it, just remember we can use the periodic table itself to just quickly determine how many valence electrons are going to be there. So group 1 and 2 are always just going to have 1 or 2 as a neutral atom. And then when we go to the P block on the right-hand side, we're essentially just ignoring the D block in the middle because those 10 groups are never going to be, the D block's always filling in one inner shell, so it's never going to be the valence electron. So that's why we're only interested in S and P. So that's why on the right-hand side, we can just do 10 less than whatever group it's in. So aluminum, for instance, is group 13. That's why it's got 3 valence electrons. That's why it's just got 3 dots there. Or chlorine is a halogen in group 17, same thing with fluorine here. So it's got 7 valence electrons. That's why they each have 7 dots there. The only exception for this, of course, is just going to be helium in group 18. Since it's in that first period, really only needs 2 valence electrons to fill its valence shell, whereas the rest of those noble gases are going to have 8. So helium would just have 2 dots, whereas argon, neon, all of the other noble gases, as we can see here, are going to have 8. And with helium, I should point out, sometimes you'll see it with magnesium as well, but with helium, since it's only going to have the 2 valence electrons, typically with helium, you wouldn't put those dots separate from one another. You would just put both of them together right at the top. Sometimes you'll see with magnesium, since both of those electrons are going into the s orbital. But with magnesium, and you can see with beryllium, a lot of the times they do separate them. But with helium, since it's kind of the exception there, we would put both of those dots just to get there. And with this, like I said, we're going to briefly talk about ionic and covalent bonding again, and then we'll mostly spend the chapter focus on covalent bonding, since ionic's a little bit more simple in terms of what's sort of happening there. But in either case, when we're forming a bond, we're going to be doing it in order to try to fill the valence shell of all these different atoms. So in most cases, that means we're going to be trying to get 8 valence electrons for these different atoms, or in the case of ionic bonds, of course, they become ions. But we're trying to get 8 valence electrons around all of these different atoms, with the exception of the first period, so hydrogen and helium. Just need 2 valence electrons. Same thing technically with like lithium. It's just going to lose one valence electron and then have two in that first period. But with that first period, since it only has that one s orbital, can only hold 2 electrons, it's the same idea. We're trying to fill that valence shell. It's just in that case going to be known as the duet rule rather than the octet rule, just because it's 2 of them, 2 electrons in that case rather than 8 of them. But again, same idea, just trying to fill that valence shell, because remember, that's going to be the most stable configuration, and everything in the universe is always trying to move towards that lower energy, that increased stability. And with these types of bonding, like I said, ionic and covalent, we've already talked about in the past. The difference between them is how those electrons are shared. So remember, with ionic, you can kind of think about the I at the start of that as sort of selfish. Ionic bonding is going to be selfish because in this case, we're going to have one element, or typically a non-metal, taking 1 or more electrons from a metal. And then when we do that, the metal becomes positive, the non-metal becomes negative, and now those charges attract the ions to one another. Covalent bonding, we'll see again, just going to be sharing electrons. So in this case, we don't have one element just taking them. They're going to be shared between both of the atoms in that bond. And then metallic bonding, we're not really going to talk about at all. But with it, it's kind of a unique one. So one of the, pretty much the only thing that the State Board of Education, or whatever it's called in New York, cared about in terms of metallic bonding when I was teaching high school, was just a mobile sea of electrons. Because essentially, if we had like a magnesium sample, gold or copper, whatever it is, with those metals, what we're going to see is we'll have the atoms next to each other. But what we'll see is the valence electrons aren't actually really going to be specific to one atom. They're able to kind of move around and sort of flow almost between those different metal atoms. That's why, again, a sea of mobile electrons, because now those electrons can move. But that's going to be the reason that metals are conductors of electricity, that mobility in those electrons, because just remember, electricity is just the flow of electrons. And with the metal, since they have the mobile electrons, they're able to pass that electric current through them. But with the ionic bonding, again, not going to spend a ton of time on this just because we've talked about it in the past, but with the ionic bonding, we're just seeing a cation, so a positive ion. Remember, with cation, you can kind of think about the T as a plus sign in the middle being positive, and then anions are negative, so a negative ion. But it's just going to be the electrostatic attraction between those two. So just remember, opposite charges attract. So when we get a positive and negative, they're just going to be drawn to one another. And if we just look at a simple example like sodium chloride, we can see sodium has 1 valence electron to begin with. Chlorine has 7, but it wants to get 8. So in order to get both of these to a full valence shell, and actually I'm just realizing sodium is missing 2 of the dots here. You can see them on the left, but for whatever reason they got removed on the right. But when sodium loses that 1 valence electron, now essentially that third electron shell is no longer there. So the second shell is already completely filled. So now sodium's got a full valence shell. And then when chlorine takes that extra electron from sodium, that'll fill its third valence shell. So now both of these have a full valence shell. It's going to be the more stable configuration. So that's what they're both trying to get to. And now these opposite charges are just going to bring them together. And with these ionic compounds, like I said, a little in one of the upcoming chapters, we'll talk more about how the types of bonds, how the structure of these different types of substances affect their properties. But because ionic compounds are going to have a fully positive ion, a fully negative ion, could even be +2 and -3, whatever it's going to be. But because we're going to have full charges there, we're going to have a very strong interaction. So we're going to see the melting and boiling points of ionic compounds are going to be much, much higher for the most part compared to covalent ones, with the exception of really, really big covalent molecules. And then with it, we'll also see some of the properties of these substances in solution as well later. But I just want to mention with ionic bonding, with covalent bonding, regardless of which kind it is, once we take a substance and bond it to something else, we've now created a new substance So we've created something with entirely new properties. In some cases, there may be similarities still. But when we think about, again, just something simple like sodium chloride on the right here, just regular table salt. Of course, we use it on food all the time to improve taste. And with the exception of like high blood pressure, it's not really going to be too dangerous of a substance at all. But when we think about sodium and chlorine in their pure elemental states, that's going to be a much different case. Because again, once we take them together and bond them, it's an entirely new substance with entirely new properties. So when we look at pure sodium, we've got pure potassium in the lab, so we can do a similar demonstration, just potassium's even more reactive. But with pure sodium, it's soft enough that it can actually just be easily cut with a butter knife. But it's so reactive, if you think about that one valence electron, it really wants to get rid of it. So it's so reactive that it actually has to be stored in mineral oil. Otherwise, it would react with the water vapor in the air and just essentially just burn, kind of. And again, we'll see a similar demonstration with potassium and water. And then with chlorine, you can see just this yellow vapor. It's going to be a highly toxic gas. So with both of these substances individually, they would be really, really nasty substances to run into. But then once again, we take them and bond them. We no longer have the properties of sodium or chlorine. We now have the properties of sodium chloride. We have that entirely new substance. And that's going to be the same with anything. And like I said, some cases there's similar properties. So like a lot of pesticides contain halogens just because the halogens like chlorine are going to be biocidal. But one of the areas where this is going to be important is going to be with vaccines. So of course with COVID, a whole bunch of nonsense came out about that, about like stupid anti-vax, whatever. But even before COVID, there was the anti-vax movement, and one of their like big pieces of like information that they would point to is that there is a small amount of mercury in certain vaccines. And mercury by itself is going to be a highly toxic substance, especially in the organic form, especially as methyl mercury. It's able to easily get absorbed into the body. It can get into the brain even, and then just have a whole bunch of negative consequences. But the mercury in vaccine isn't that form of mercury. It's going to be in a different compound. So it's going to behave completely differently. It's not going to behave like elemental mercury. It's not going to behave like organic mercury. So the effects are going to be much, much different. And then additionally, the amount of mercury in that vaccine is also going to be extremely minor. So it's going to be for multiple reasons, not really anything to worry about. But again, with the anti-vax, they're not the most scientifically literate community. So they try to just take any piece of information and twist it how they can to fit their beliefs. But going back to the ionic compounds, with them, we wouldn't really ever say we've got a single ionic molecule, because when we actually look at a sample of an ionic compound, again, just using sodium chloride because it's a very simple compound. With this one, you can see chloride, I should say, in green, and then that sodium ion in purple. But then you'll also notice this sodium ion is bonded to multiple, or it's attached to multiple of the chloride. And then the same thing with the chloride, they're attached to multiple sodium. So with these ones, because it's just the opposite charge is attracting, there's going to be multiple pieces attracted to each other. So with the ionic compounds, that's why we use the simplest ratio. So with like sodium chloride, we would just say NaCl. We could say Na3Cl3, still showing you the same ratio. And if we look at a certain portion of this molecule, we may have them in that ratio. So for instance, if we actually just look at kind of this half of the front face of this crystal, we'd have 3 sodiums and 3 chlorines. But they're all attached, they're all bonded to different ions. So we wouldn't really say that we've got just like one specific molecule. So we wouldn't just refer to the ones that are labeled as like, this is one molecule and this is another. It's just going to be sort of a larger sample of sodium chloride with those atoms just sort of interspersed. And with it, depending on the charge, depending on the size of those ions, that'll actually determine the shape of the crystal. So with sodium chloride, we may see something like this, where it's just sort of a pretty standard, just sort of repeating pattern, because they're roughly the same size. They're just +1 or -1, so we just need a 1-to-1 ratio. But if we had ions that were where one of them is much bigger than the other, or where we've got different charges, so if it's +2 and -3, then we're going to need a different ratio of those ions. The way they space out is going to be different, so that's going to determine the crystal structure. And there's certain chemistry classes that get more in depth with that. Particularly if you take like an inorganic chemistry or a crystallography sort of class. But with this, just to go back to one of the earlier chapters again, remember we can use the periodic table to determine what the charges of these elements are likely to be in a binary ionic compound. So remember, binary just referring to 2. So like binary code is just 0s and 1s. So binary ionic compound is just going to be an ionic compound that contains 2 elements. So with the metal, remember we've got the staircase kind of going through this section. And then to the right of it, we've got our nonmetals. The left of it, we've got our metals. So the metals are going to lose those electrons. So lose 1, lose 2, lose 3 in the case of aluminum. If you think about lead and tin, they can form +4 ions just because they'll lose those S and P electrons. With the transition metals, though, we typically need more information to actually determine the specific charge on them. Some of them, like zinc and cadmium, are always +2, silver is always +1, but things like iron, cobalt can be multiple, so we have to have a little bit more information with those. But then with the nonmetals, we can essentially just look to see how many spots do we need to move to the right to get to that noble gas group, because that's how many valence electrons they're going to have to gain. This isn't always going to be the charge, but in a binary ionic compound, we can pretty safely assume that would be the charges here. Because with fluorine, chlorine, bromine, iodine, all just have one missing valence electron. So they're just going to gain 1 more, whereas oxygen needs 2. So it's going to be a -2, nitrogen -3. And when we're looking at ionic bonds forming, we think about starting with those pure elements and look at it from an energetic standpoint, we can kind of see the different pieces here and why forming this bond is going to be preferred. And if we start with the sodium piece of it, again, starting with a sodium metal, it's got that 1 extra valence electron that it wants to lose. So it wants to get to Na+. So in order to balance this, we've got 1 sodium on each side. But now if we've got a positive charge here, we need an electron to balance it off. So this is just saying going from sodium and then having it lose that electron. It's going to take 495 kilojoules to remove that electron from a mole of sodium. So we're going to have to input that energy. But then from the chlorine perspective, going to chloride, now it's going to accept that electron. So this is kind of, if we think back to the previous chapter, this would be ionization energy. This would be electron affinity. So chlorine wants to gain that electron. It actually releases energy in the process, releases almost 350 kilojoules for every mole of chlorine. But when we look at those two together, we had +495, -349. So we're going to wind up with +155 kilojoules overall if we just think about those two processes together. But if we were actually to take chlorine gas, add a sample of sodium to it, what we would see is that's an exothermic process. So the delta H would actually be negative. You can see it's giving off this energy in the form of that light, that heat. But it's going to be giving off that heat. But based on the processes of sodium losing an electron, chlorine gaining one, we're missing some component of this. And what it's going to be is the interaction now between those actual ions. So if we think about it, up to this point, we looked at the energy to go from a sodium atom to a sodium ion. And then we did the same thing for chlorine. But that had a positive delta H overall, because this needed more energy than this released. So we had a little bit over 150 kilojoules from those two processes. But what we're missing is what's known as the lattice energy. And it's just going to be the electrostatic attraction now between those two ions. So you can kind of think about forming those ions And then when we have them, they're going to be drawn together. That's going to be kind of a stabilizing force, a stabilizing interaction. So forming that bond is also going to release energy. So just remember, forming bonds releases energy. So that's going to be the third piece here that actually makes this an exothermic process overall. And I think sometimes thinking about bond formation releasing energy doesn't make the most sense. But if we think about breaking a bond, the opposite of forming one. If you think about just a pencil, if we want to snap that pencil in half, we're going to have to put energy into it in order to break it. It's kind of the same thing with the bond. If we want to break that bond, we've got to put energy into it to sort of make it unstable. So if adding energy breaks a bond, that's just going to be why the opposite occurs when we form it. That's actually going to release that energy. It's going to be making it a lower energy scenario for those atoms or ions, whatever it is, depending on the type of bond. But actually, to go back here for a second to look at this equation, we're not really going to be calculating lattice energy a ton. There may be a question here or there, but for the most part, we're just using this to kind of identify that third piece, the third piece to make this a exothermic process overall when we form the ionic bond. But with it, K is just going to be a constant. So that's just going to depend on the crystal structure itself. So we can kind of just ignore K. That's just going to be some value. But if we look at Q1, Q2, and then D, we can get an understanding of the values on this next slide. But Q1 and Q2 are just going to be referring to the charge on those ions. So it would be like +1, -1 for sodium chloride, +3, -2 for aluminum oxide. So as we get the charge's larger magnitude, we're going to be multiplying by larger numbers. So the lattice energy is going to increase. Essentially just saying if we've got larger charges, we're going to have a stronger interaction for that ionic bond. And then with the distance, if you think about it, distance is on the bottom. So as we divide, if we make distance larger, as we divide by a bigger number, that's going to make the lattice energy smaller. So if we're thinking about increasing the strength of this electrostatic attraction, we want to either increase the charge of those ions. Larger charges is just going to be a larger interaction overall. Or we want to take those charges and just move them closer together. So if we decrease the distance, well, now we're dividing by a smaller number, ultimately going to give us a larger lattice energy overall. But now if we look at the table here, we can pick a few examples and kind of see what's going on here. And let's just see if I can get the pen. For this, let's just highlight. Whoops, that's a terrible highlighter. Okay, I thought that was going to be the highlighter. Switch back. Yeah. So for the lattice energy, if we look at those two with magnesium chloride, we can see why the lattice energy is much larger with magnesium chloride. So with sodium fluoride and sodium chloride, in each case, sodium is going to be +1, and then fluorine and chlorine are halogens, so those would each be -1. So when we're thinking about that lattice energy equation, in each case, Q1 and Q2, when we're comparing these two together, would be the same. So the only thing that's going to be different between them is just going to be that distance on the bottom. But because chlorine is in the third period, fluorine is in the second, the chloride ion is going to be larger than the fluoride ion. So when we look at the interaction between these two, you can think about sodium and chlorine are going to be further apart than the sodium and the fluoride will. So that's why we're just going to see sodium chloride is going to have a slightly weaker interaction there, slightly lower lattice energy. And then going over to magnesium chloride now, magnesium is going to be roughly the same size as sodium. There will be differences, but it's not going to be anything super extreme. But when we look at the lattice energies here, we can see magnesium chloride is about 3 times higher. And the reason for that is because now we're going to have different charges here. Now the magnesium is going to be +2. Chloride's still going to be -1, but we've changed the charge on the cation. So now that we've changed that charge, we're going to have a different K value, just because the crystal structure is going to be different. But now we've got a larger charge there. Magnesium also would be a little bit smaller than sodium, so because it's got an extra proton, but it's going to have the same electron configuration, so they would just get pulled in a little bit more. So it does help that magnesium's a little bit smaller. But the main thing here is just going to be that increased charge on magnesium compared to sodium. And then if we look at magnesium oxide, calcium oxide, strontium oxide, now we've got a +2, -2 charge. So that makes sense why all of these are going to be larger than these ones. Now we've just got larger charges. Same thing with scandium nitride, we'd have +3 and -3. That's why we got an even larger value here. But then if we compare these three together, the reason it decreases as we go from magnesium to calcium to strontium is because those charges are going to be the same, but magnesium is going to be smaller than calcium, which will be smaller than strontium. So just the distance is going to be the important piece there. And then if we look at the diagram here, this kind of just walks us through. So you can think about this, where the green arrow starts as kind of our starting point, and then ultimately we're forming sodium chloride. So you can see the overall change is going to be negative. But if we follow it, we can look at it kind of piece by piece. So sodium as a element is going to be a solid. But in order for this to take place, we need to get it in the gas phase. So it's going to be increasing energy to go from solid to gas. And then if we think about the chlorine, it's diatomic in the elemental state. So in order to get it to react, we're going to first have to separate out those chlorine atoms from one another. So instead of Cl2, we've got to get it to Cl. And again, that's going to take energy. Now that we've got the individual atoms, we need sodium to lose that electron. And as we saw, it's going to take some amount of energy to take that electron from sodium, excuse me. But now once we get to this point, chlorine, we saw the electron affinity had a negative delta H there. So when chlorine now takes on that electron and forms chloride, that's going to release energy. So now we're seeing it decrease. And then the final piece that gets us to sodium chloride overall is now we've got the positive sodium, the negative chloride. So we're going to form that sodium chloride bond, that ionic bond. And remember, forming bonds releases energy, so that's why we see the big decrease here. And again, if we had a +2, -2 ion, this decrease would be even larger, just because that lattice energy is going to be even greater in that case. It's going to release even more energy when it forms that bond. And with this, if we think back to the ionization energies, we saw that different groups had like a big jump between either the first and the second ionization energy for the alkali metals, or the second and the third for alkaline earth metals. We can use the energy here to understand why we're not going to form like a sodium +2 bond, or sodium +2 ion, is because when we then had to remove a second electron from sodium, it's going to take almost 10 times as much energy as it did for the first one. And in that case, if you think about it, this step is going to be much, much higher. It's going to go 10 times as high. So the lattice energy, if we were to form an ionic bond in that case, just wouldn't be great enough to overcome the additional energy required to remove that second electron. Or in the case of magnesium, you can see here, second to third, we see a big jump. So it would just be the same idea, just after that second electron for magnesium. And then with covalent bonding, in this case, we're going to see it's sharing electrons. So with ionic bonding, like I said, you can think of it as kind of selfish, because it's going to be a transfer. One of those atoms is fully going to take the electrons from the other. Whereas in the covalent bonding, we just break down that word. Co, kind of meaning cooperative, working together. Valent, just referring to the valence electrons. So they're going to be sharing those valence electrons. And we can see just a generic example of that here. So atom A and B both have 7 valence electrons to begin with. But remember, we want to satisfy the octet rule. We want to get to 8. But if one of them just takes the electron from the other, So if atom A was to take this electron from B or vice versa, the atom that took it would be fine. It would have all 8 that it needs. But then the atom that lost it would only have 6 now. So with the covalent bonds, the reason this is going to satisfy the octet rule or the duet rule in the case of hydrogen is because these shared electrons now count towards the valence shell of each of these atoms. So if we look at the molecule here, atom A and B each have 6 valence electrons on their own. But then these two shared count for A, they also count for B. So atom A's got 6, and then it's got the 7th and the 8th here. And then atom B, same thing, it's got 6 on its own, and then the 7th and the 8th also count for atom B. So that's why both of these are now going to be satisfying the octet rule. That's why these covalent bonds are going to form. So the big thing is just recognizing that those shared electrons count towards both atoms' valence shell. And with this, we'll talk about more in depth in the next chapter on what's exactly happening with the covalent bond, because depending on the orbitals, depending on the atoms and things, different types of covalent bonds can kind of form, and we'll, like I said, we'll get into it more in the next chapter. But essentially what's happening is as we have these atoms, and we're thinking about just hydrogen here, so each of these circles just represents a hydrogen atom. As we have them some distance apart, there's going to be no interaction. So once we get them further enough apart, there's just essentially no interaction between the two. So that's why you can see the energy is 0 all the way to the right. They're just far enough apart that they're not really doing anything to one another. But as we start to have them get closer and closer together, so you see the internuclear distance, just the distance between those nuclei. As we move it to the left, as we push them closer and closer together, what we're going to see is that those orbitals are going to overlap. So remember, hydrogen just has 1 valence electron. So each of these atoms has an orbital with 1 electron, but it wants to get a second. So these orbitals are just going to start to overlap. And in that process, it's going to kind of be a stabilizing force. That's why we see the energy decrease. But eventually we get to kind of an energy minimum, the lowest point here. And what this is going to be is the actual bond length, because this is going to be the distance where these are the distance apart for these two atoms, where the energy is just going to be the lowest. Now, if we start to take them and push them even closer together, you can see the energy just skyrockets again. So it's just not going to have the proper orbital overlap, essentially. And that's why we'll see with hydrogen, for instance, the typical bond length is going to be 0.74 picometers. If we had 2 different atoms rather than hydrogen, the bond length is going to be at a different length. But it would still be kind of the same idea, where as we move those atoms closer and closer together, eventually we hit an energy minimum, and that's just going to be the bond length itself. And with this, like I said, we'll go into the properties of these substances later on, but I just wanted to put this here because with the ionic substances, we can more or less kind of apply just a general set of properties to those ionic compounds. There are some differences in terms of solubility and things like that, but for the most part, those ionic compounds are all going to be relatively similar to one another. Whereas with the covalent ones, we're going to see there's kind of different categories, and depending on how the bonds are formed, depending on what atoms we have and where those atoms are, is going to have a bigger impact on their properties. So that's why in this case, we've got non-polar covalent substances, polar covalent substances, and then we'll even see regardless of which of these it is, if it's just a really big covalent substance, those will have kind of their own set of properties as well. But like I said, we'll as we go through this, figure out how we can go from the formula to the structure, and then from the structure to the properties of that substance. But with the polar and the non-polar covalent bonds, both of them are still going to be covalent bonds. So both of them are still going to be sharing electrons. So you can see in each of these cases, we've got 2 shared electrons between each of those atoms. It's just with the non-polar covalent. If we think about both of these atoms being the same, and think about this as kind of a tug of war, both of these atoms are going to be the same. So they're going to have the same strength. They're going to have the same affinity for those electrons. So neither of these atoms is going to be able to pull those electrons closer to itself. So with the non-polar covalent bonds, we have an equal sharing. And because of that, we can kind of just consider it to be neutral. there's no positive or negative piece because the electrons that are being shared are right in between, right in the middle of both of these atoms. Whereas if we've got two different atoms now, we'll say in this case, atom B has a stronger affinity for these electrons. So we can see B is essentially, if you think about it again, as a tug of war, pulling those electrons closer to itself. So now because the electrons themselves are negative and they're closer to atom B is going to be partially negative. So that little squiggly sort of S symbol just stands for the partial charge. So partial charge negative on B. And then because this is going to be a neutral molecule overall, if atom B is partially negative, that means atom A has to be partially positive. And the reason this is called a polar covalent bond is kind of the same idea as planet Earth. We've got the north and the south poles, so we've got opposite ends. It's kind of the same idea with these molecules. It's just instead of north and south, now we've got partially positive and partially negative ends. But because we've got those two distinct charges now, whereas the nonpolar is just neutral, that's why we're referring to it as a polar bond. And if we look at hydrogen chloride or hydrochloric acid, we can see the same thing. So we'll figure out in a couple slides, or maybe even the next one, why chlorine is going to be the negative one compared to hydrogen. But with these two atoms now, they're sharing electrons, but chlorine's going to have a stronger affinity for those electrons. So we'll see chlorine's going to be partially negative, hydrogen's going to be partially positive. So another way of showing this is just what's known as the dipole moment. So dipole, we just break down that word pole, so referring to two ends, positive and negative, and then di just because we've got two of them, so the positive and the negative. With these arrows, they're just vectors, so they show the magnitude, they show the direction. So a larger arrow just means it's going to be a larger charge, larger negative charge, and it's going to be pointing in the direction of that negative piece. So since chlorine is our partially negative one, that's why we've got the arrow going in that direction. But again, like I said, if we had two bonds here and one of them was more polar than the other, we would just have a bigger arrow for the more polar one. And in order to determine which of the atoms in a polar covalent bond is going to be positive or negative, we can just use electronegativity values. So this is going to be a similar idea to electron affinity. But whereas electron affinity is kind of specific to the gas taking an electron, this is just going to be the tendency of an atom to attract shared electrons. And with it, you can't actually measure electronegativity directly. So there's like calculations people do to get these values. And there's a couple different calculations that people have, but Pauling is the kind of the standard, the most common one. So you'll notice at the top right, fluorine 3.98. It's going to be our largest value. Oxygen 3.44, nitrogen 3.04, chlorine 3.16. So we've got values over 3 to the top right. And then as we move away from that direction, as we go to the bottom left, you can see francium 0.7, cesium 0.79, radon, or radium, excuse me, not radon, radium 0.9, 0.89. So we can see much lower values to the bottom left. And that makes sense because if we think about the metals, they want to lose electrons. So they're not going to be good at pulling in others. Makes sense that they're going to have really low electronegativity values. And then fluorine, very small atom, missing just one valence electron, so it really wants to gain one more. So it makes sense why fluorine's going to be able to pull in electrons more. So with the electronegativity, we're just looking towards the top right, we're looking towards fluorine. And then remember, we're going to exclude, just like with electron affinity, we're going to exclude group 18, just because they already have a full valence shell. So they have no tendency to pull in electrons. So if they actually included group 18 in this graph sometimes, they'll usually just put like a line just saying that they have essentially no electronegativity. But with this, there's going to be kind of a spectrum in terms of the difference in electronegativity between the atoms in a bond. And depending on the difference in that electronegativity, that determines kind of what type of bond it is. And with all of these bonds, whether it's non-polar covalent, polar covalent, ionic, they're all kind of the same idea, just to different extremes. So if we think about a pure covalent or a non-polar covalent bond, that's going to be shared evenly. The polar covalent bond, now we're still sharing it, but it's uneven. One of those electrons is pulling it in more because it's going to be more electronegative. And then with the ionic, we've just pushed it even further to the extreme. Now that atom, instead of just pulling it in a little bit, now it's completely taken that electron. So if we knew what two atoms were involved, if we knew the electron negativity values for those, we could just look at the difference. And if it's greater than 1.8, it's ionic. If it's less than 0.4, it's a nonpolar or a pure covalent bond, like the textbook calls it. And then if it's in between those two, that would be a polar covalent bond. And then you can see with the polar covalent bond, it's a range, because if we had a difference of 0.5, that would still be a polar covalent bond, but it's going to be much less polar. Those partial charges are going to be much smaller than if it was a electronegativity difference of 1.5. In that case, the more electronegative atom would be pulling in that electron much, much more. So we'd wind up with larger charges there. And then just to visualize this a little bit, like I said, it's kind of just taking it and pushing it to an extreme as we go from non-polar covalent bonds to ionic bonds. So with these types of diagrams, what they're showing is what's known as electron density. So blue is going to be where we have a lot of electrons. It's going to be a negative charge. Red is going to be where we're lacking electrons. That'll be a positive charge. And then the grayish white is just kind of neutral. So when we look at a non-polar bond, they're sharing these electrons evenly. So what we see is everything's kind of balanced out. We just wind up with a neutral, neutral bond, neutral chlorines, in this case for the diatomic. But then with hydrogen chloride or hydrochloric acid, we see chlorine's going to be more electronegative than hydrogen. If we go back to the table, chlorine 3.16, hydrogen 2.2. So we've got a difference of about 1 there. Right in the middle of our polar covalent category. So it makes sense that we see chlorine be partially negative. It's pulling those electrons in more, which means the hydrogen, in order to balance it, just has to be partially positive. And now with the sodium chloride, kind of the same idea. It's just once we replace hydrogen with sodium, now chlorine's able to just essentially completely grab those electrons. And now we've got a chloride ion, we've got a sodium ion. So that's why we've just got these two ions totally separate now. So we've got a fully negative chlorine and a fully positive sodium for the ionic bond. Whereas the polar covalent, we've only got a partially positive hydrogen, a partially negative chlorine. So it's just not going to be quite as strong of an interaction there. And when we look at the halogens with hydrogen, we can kind of see that same thing. So as we're moving down that group, as we move from fluorine 3.98 to chlorine 3.16 to bromine just under 3, iodine 2.66, we can see that electronegativity is decreasing. So the difference between fluorine and chlorine or bromine with hydrogen is going to decrease as well. And that's why we can see the electronegativity difference. In this case, it looks like yellowish green is going to be kind of the neutral. Red will still be negative. Blue will still be positive. But as we go from fluorine, very electronegative, so we see pretty dark colors there. Chlorine, still pretty electronegative, so we see roughly the same thing, but it's not quite as electronegative. It's a little bit bigger too. So it's just not as polar. But then when we get to hydrogen bromide and hydrogen iodide, we see that the electronegativity difference has decreased, that this is barely kind of polar. This is pretty much right on the cutoff between polar and not. And that's why we don't really see any red. We barely see a little bit of kind of bluish here. You can see with the bromine, there's a little bit more of the red in there, just because it's a little bit larger of an electronegativity difference. But again, we can just see as the electronegativity changes, the polarity of these molecules change, even though the structure is going to be essentially the same because we're just taking a halogen and changing the halogen each time. So with this one, we'll look at, let's see, we'll just look at this slide here. So if we want to figure out which of these bonds is most polar, we've got a boron with a chlorine or a carbon with a chlorine. And then with the second set, we've got, I don't know why there's a C, but with the second set, we've got a phosphorus with either fluorine or chlorine. So with the first one, if you think about it, in each case, we've got a chlorine. So that's not going to be the determining piece. That first atom is, we want boron or carbon. So we want to think about which of those is going to give us a larger electronegativity difference with chlorine. So essentially what we can do is just think about which one's going to be further away from chlorine. And since both of boron and carbon are period 2, but boron's group 13, carbon's group 14, boron's a little bit further away. So boron's electronegativity is going to be a little bit lower than carbon's. So the difference between boron and chlorine is going to be a little bit greater than it would be for carbon and chlorine. So boron and chlorine will be more polar. And then similarly, since the phosphorus is the same here, we want to think about which of these, fluorine and chlorine, is going to be more electronegative. And since fluorine's the most electronegative, it'll just have to be PF. And again, if we look at the table here, so for the first one, chlorine with either boron or carbon, so 2.04 to 3.16 or 2.55 to 3.16. So with boron, it's just a bigger difference. So it's going to be a more polar bond. Chlorine's going to have a better hold on those electrons. So chlorine's going to become more negative, meaning boron will have to become more positive. And then kind of the same idea with the second one, we've had phosphorus in each case. But now we're taking phosphorus and either putting it with fluorine or chlorine. And with the chlorine, it's got a difference of about 1. With the fluorine, it's just a little bit under 2. So it's just going to be a larger electronegativity difference there. We're just going to see a more polar bond because of it. And then with the next part of the chapter, we'll start to look at, like I said, these actual Lewis structures.